Welcome to our OpenPOWER Academy and Research Big Data and AI webinar series. This has been a successful webinar so far. We have been having lots of participants. Every webinar, and I do see right now there are like 145 people participating as part of this webinar. And thanks for joining the webinar today. And my pleasure to have you all here. Today we have Dr. Sunita Chandrasekaran from University of Delaware and Clarisse Hedglin from IBM to share their experiences on big data, AI, and cloud platforms. And we have our special guest also as part of panelists, Professor Arghya Das from University of Wisconsin, Platteville, and also Professor Senthil Murugan from SRM India, going to be sharing their experiences too after the presentation, and also asking questions and all the stuff, making this webinar more interactive. And then today's sessions will be recorded and shared. Q&A will be end of our first as well as the second presentation. You can raise your hands as well as you can post questions in the chat window. Our first talk going to be given by Dr. Sunita Chandrasekaran, and she'll be sharing about OpenMP offloading, validation and verification test suites. Sunita Chandrasekaran is an assistant professor with Department of Computer Science and Information Sciences, University of Delaware. Our area of research spans across high performance computing, computer architecture, parallel programming, and exploring challenges with migrating legacy scientific code to accelerators and heterogeneous processors. And she has got, a good years of experience, with the high performance computing and the team too. Professor Sunita, please go ahead and start your presentation.
Thank you very much, Ganeshan, and for organizing this webinar series. We are in unbelievable times, and it's really wonderful to see us, proceeding as usual with Zoom and webinar. So thank you, IBM, and everybody involved, to make this happen. My special thanks to everybody in India who have dialed in during this evening time of yours. So thank you for your time. All right, so today I'm going to tell you about a particular project involving OpenMP, and this is about the validation and verification test suite of OpenMP programming features. I have a website in the title. CRPL is my lab, Computational Research Programming and a lab. So CIS.udel.edu, OMP VV Solve. Solve is the the main project umbrella. We will look into it in a minute. And ECP stands for Exascale Computing Project. So the website is specifically for the validation verification test suite effort. And the collaborators include people from Oak Ridge Lab, Swaroop, Oscar and David, and from my group, Josh, Thomas, and Jose. Jose recently graduated on this particular topic with a master's and a thesis. Josh is my undergraduate student, and Tom is going to be my master's student in fall 2020. So that's our group, as you can see. Plus, we talk with a number of vendors, including IBM, AMD, Intel, on various different topics with respect to this particular project. All right, so let's kick off. What is this project about? My main goal or motivation out of this project is to create awareness that this project exists. What are we doing within the project? It's also open to collaboration because it's an open source test suite. So the goal is to let you know what we are doing, how to access the tests, and where are we with respect to the testing of OpenMP suite. So SOLVE stands for Scope and Intent of the, oh, sorry, that is not what SOLVE stands for, but SOLVE is the bigger umbrella ECP project. I'm going to show you a little picture in a minute. And this particular project falls under SOLVE. And as part of the validation verification test suite, today we will look at the design of the test, infrastructure, and a couple of case studies to give you an idea of what are we testing, some results, and links and information for you to look into when you want to probably get involved in any capacity you would like. Right, so that is the bigger picture, OpenMP programming environment for Exascale Computing Project. And exascale computing project, as you might know by now, it's a massive project. All of us are gearing towards creating better software, better hardware, better co-design frameworks, to ensure that we are ready when the exascale computers are falling in place, which is going to happen very soon. So you can see the different, boxes in the picture, and where we belong to is, if you can see my cursor, unit testing, validation suite, multi-platform testing. So that's the part of the bigger project. So there are other collaborators working on the different aspects of ECP Solve itself. There is a little link to Solve. It's from Brookhaven National Lab. And Barbara Chapman, from Stony Brook and Brookhaven National Lab, as a PI of ECP Solve. And there are, as I said, many different people involved to bring this together. The scope and intent of V&V, so I'm going to call it V&V as a short form for Validation Verification Test Suite, is to validate OpenMP compiler implementations for target architecture. By that, I mean OpenMP has been existing since 1998, if I'm correct, 1997, 1998. So it's been there for a long, long time, right? And for a long time, until 2013, OpenMP was predominantly targeting CPU, and ever since 2013, OpenMP ratified programming features to target accelerators like GPUs. So this scope of this particular project focuses on the OpenMP compiler or programming features that target accelerators. So that is what I mean by target architecture. So when I say target architecture, I actually mean accelerators like GPUs. So we are testing OpenMP 4.0, that is version 4.0, version 4.5, and version 5.0. So these are the versions that have been targeting GPUs from the OpenMP standpoint. All right, so verifying the implementations of its conformance to OpenMP standard. By that, I mean there are several compiler vendors implementing OpenMP features, right? So there is Intel, there is AMD, there is IBM, LLVM, Clang, GCC. So there are a bunch of vendors. So how do you really verify that the implementation of, say, Pragma OMP parallel, right? How do you know that Pragma OMP parallel is doing the right job? So that's the whole point of testing the suite. And in that context, there are many different other things that comes into place, because there are definitions in the OpenMP specification, which is over 500 pages now, of what is a particular definition of a particular feature. So you look at the definition, you look at the implementation, and you write a test which verifies the implementation's conformance to OpenMP standard. So we're going to look through how we do it, because as you can see, there's a lot to do here, right? The project is also driven by ECP, Exascale Computing Project's usage of OpenMP. OpenMP is predominantly one of the main directive-based programming model for ECP projects and other projects. Like I'm in academia, so I use OpenMP very heavily as well. And so do, I'm sure, several of you on the call also use OpenMP for many different aspects. 5.0 features are in place as we speak. Implementations are rolling in, and sometimes we write tests for implementations that don't exist. So that, that becomes a challenge. And sometimes we write implementations, for features that do exist to, verify and validate and report results to, the vendors and anybody using it. So at the moment, I cannot guarantee that that is the entire list, because as we talk to others, there are many people using the test suite. But I'm really happy and grateful to all these collaborators who are using our test suite currently for conformance and regression testing. ORNL stands for Oak Ridge National Lab, which is in Tennessee in the US. Lawrence Berkeley National Lab, also another national lab in the US. AMD, Intel, Cray. Argonne National Lab is in Illinois. So all of them are currently using the test suite for conformance and regression testing, and we gather this knowledge as well. We get pull requests from GitHub, and then we match up to, okay, so who is looking for a pull request, right? Apparently, work in progress to integrate the test suite into the LLVM test infrastructure, from what we hear. And someone is also using NEC SX Aurora system with the test suite. So as you can see, the users are varied, right? They are spanning labs and vendors, and we know that RWTH Aachen in Germany recently published a paper citing our test suite, and we contacted them, and we were very glad that they were using the test suite for their internal projects and testing. So that's the workflow where, imagine you are the user, right? The user specs as guide for implementation. So this is the specification picture, if you like. And suppose this person is the compiler implementer, the compiler developers, and say this person is the user. So say I am the user and you are the compiler implementer, or vice versa. What really happens is, as an implementer or a developer of a compiler, you would go and read the specification to understand the definitions of the programming features. Myself, as a user, would also go and read the specification to see, so how do I use this particular feature, right? So the implementer is looking at the specification to implement a feature, and I am looking at the implementation to use the feature, right? So one of the questions that I would love to know from the audience we got today, we have about 208 participants, is how many of you are users? How many of you are developers, right? So what I do as a user, I use systems for programming the platform. It could be any system. It could be systems with only CPUs. It could be system with CPUs and GPUs. It could be anything, right? And the developer or the compiler implementer tries to implement this feature to as many platforms as possible. That's why the catch is, because you can't satisfy everybody, nor can you, target all different platforms, right? So how do you guarantee a system compliance with the compiler and programming model? It's one of the questions. How do you guarantee an implementation's compliance with the specification? As in, who says my implementation is correct? Or who says that I, as a user, are using it as I'm supposed to be using, right? So all sorts of questions. And once you get into the nitty-gritties, there are many different aspects to answer before you can say that, okay, this is, this particular implementation that actually really works. That's a test design process to give you an idea of where we start to where we end with the particular test. So for starters, we look at the OpenMP 4.5 offload directive or a feature, or we look at an application that uses 4.5 offloading directive. So it could be just a directive, or we could look at it from an application standpoint. Then we look at, so this is a Pragma OMP, parallel. I'm taking parallel as an example because I'm pretty sure most of you would have used it for the time being. So imagine that I'm formulating a test for that, right? Then we discuss internally, we have these weekly Wednesday phone calls with Oak Ridge Lab, where we discuss the validity and adherence to the specification. Now, I may interpret the specification a certain way, you may interpret the specification a certain way. I can't say that I'm right, neither can you say that you're wrong, right? So there's a lot of discussions that happens to understand what is the correct interpretation of the specification. So here is where a lot of hiccups come in. The compiler developer interpreting the specification to a certain way, the user interpreting the specification another way, and we as test creators, we'll end up interpreting the specification in another way, right? So you can imagine that there are already 3 versions of interpretation of the specification. Anywho, so then we write a valid test. If the test is a valid test, if the team agrees that this is a valid test, which is the yes here in this flowchart, follow the yellow line with me. We test it with the available implementations. The available implementations include compiler implementations of, say, IBM, of, say, AMD, Intel, what have you. If the test passes, which is a yes, we open it for review. In the sense, we put it out within the Oak Ridge and UDEL team. And because this is a GitHub process, right? If I create a test, I can't declare that my test is correct. You have to open it up, somebody else reviews. So rule of thumb of a software engineering project, you don't write the test and you don't get to review your own test. That's, rule of thumb. So you pass it on to your colleague and you say, hey, look, I wrote a test, do you mind reviewing? If the test is accepted, we add it to the validation verification test suite. Now let's go back to this end. We wrote a valid test and one of us disagrees that what you have written doesn't make sense. So, I'm saying it is not a valid test. So I go back and look at the formulating test step once again to see why is not a valid test. Some back and forth conversations, then we'll end up agreeing. Then we discuss validity, once again, adherence to specification, valid test, yes, and then we get to test with our available implementations. Test passes, great, open for review. Test accepted. If yes, we go down this path. What if the test is not accepted? And that happens very often. So the test is not accepted. So one of them says, you wrote a test, it passes, but well, I don't think the test is written in the right way. So that becomes a no. So we go back to discuss the validity and adherence to specification, because if I wrote the test, the way I wrote it may be incorrect, and maybe you would come back and say, okay, look, you haven't written this correctly, we need to discuss. So that is this step, right? So you go back and then you again go through validity, test with available implementations, test passes, open review, blah. Now, if the test does not pass, that is a major thing, right? And this is where most of the times we get stuck at, because rarely does a test pass and everybody agrees and it goes to the suite, right? Because the whole purpose is to find bugs. So the point of writing this test is to find bugs, to find ambiguities in specification. So it's not a hunky-dory process, basically. So you write a test, and if it does not pass, the question is it a specification issue? Did the compiler implementer implement the feature in a certain way, but the specification defines the feature in a certain other way? So at that time, what we do is, when our team disagrees to each other, we bring it forth to the OpenMP group. It's a large, massive group with a ton of interested stakeholders. And we either put it in an email, or mostly we have been using the OpenMP email alias in University of Delaware as a member that allows me to contact OpenMP developers and users to talk about stuff like this. So I bring it to them and we discuss, and with the help of experts, we further decide which process to go through. Now, in the event the test did not pass and it was an implementation bug, which means the specification people are happy and the test is correct, but the compiler failed, right? So we go to the compiler vendor and we report a bug. So naturally, compiler is not a magic tool, right? We all know that by now. So we have to build a robust compiler. How does a compiler become robust, mature, and stable? By actually going through this entire process of finding issues, fixing it, finding issues, fixing it. So as the versions improve, or the versions, there is version 1.0, 2.0, 3.0 of the compiler, by the time it has passed through, say, 10 versions or X number of versions, you almost get a good compiler to use because it has gone through this rigorous testing process. I do want to point out that our test suite is not the end all, right? Vendors have their own test suites. They have their own testing process. So this is not the deciding, our test suite is not the deciding criteria of a particular compiler. Compiler vendors have their own stuff going on internally. What we are perhaps doing is enhancing the testing process by giving them more information, just so that their internal test suites are not biased in any which way, because we are a third party, right? And we don't have a vested interest in any of the compilers that we use. Our goal is to test the compiler. That's the bottom line. Anyhow, so I hope the flow chart is making sense to you, and I hope you have the nice overview of how we deal with this project. All right, so understanding the specification, I'm going to give you, I think I have 3 examples of what do I mean by writing these test cases, and when do we say that something is correct and something is wrong. Now, this is probably 1% example of the massive amount of tests that is out there. So this is just an example where you are looking at 2 code blocks, right? The top and the bottom. It has nested pragmas in it. So you have pragma OMP target data map, and you have pragma OMP target teams distribute. So 2 different blocks. They both specify a data mapping over an array section. The only difference being the portion of the array, 0 colon array underscore size here, 0 colon 02, array size by 2. The first one is the entire array. The second one is only half of it. Now, this might make you wonder, okay, which one is correct? Which one is the right way to do, right? And we have done this, we have done this. We have failed with the compiler bugs. We have gone back to the vendor. We have read the specification. But naturally, if you want to only use a portion of the array, you would tend to do this, right? However, the first one is the one that is correct. Now, if we were sitting in front of each other, I would have probably asked you guys to, put a hands up and say, okay, tell me which of the code block is correct. So we can't do that right now. So I'm showing you the answers. So what happens here is, specification doesn't explicitly mention, the requirement or, how exactly you would deal with this particular code base. But having looked through the specification, you can obviously, it's very evident that you can use the map clause, and then be able to use any portion of the array size. So this is many a times interpreted differently by different vendors. And there are different compilers that compiles it throughout perfectly. Some compilers may, define a bug, compiler error, explaining the problem. Some compilers may fail at the runtime, but that is what the test basically catches. So this is an example of, how is the concept of understanding the specification. The next is another twist to, how you interpret the specification, right? So here, as you can see, here we are pointing out the ambiguity in specification. And this is something that we have, discussed with OpenMP. And over here as well, the second one is prone to work correctly than the first one, because the above restriction means the item share cannot appear in both the shared class as well as the map classes together. So we used this way in the beginning, and obviously it didn't work. So the workaround is to use default map, but the effect or the output is pretty much the same. So this is later fixed in the OpenMP specification because how we interpreted it, and we started writing a test case like this. Obviously did not work, but that's how we interpreted the specification, this is a particular line number from the specification, page number 218. Things move around, so if you don't look up, if you don't get this particular line in 218, just look around it. Another piece is a compiler bug where you can see a no wait clause. It's a simple bug that the test suite identified. This particular code block has two distributed loops within a map region. So you have the map region here, you have two distributed for loops. The first loop has a no wait attribute or the feature or the class. And this compiled on GCC 8.1.1. GCC has a 9.1 version, but it threw a runtime error complaining about an unimplemented feature, which is weird, right? So that's the error we got with GCC 8.1.1, that this particular thing is unimplemented. So that's the other piece. The features that are in the 500 pages book of specification, especially the recent ones, 4.0, 5.0, not necessarily that you would find the implementation in a vendor, because it's all work in progress. As we speak, the vendors are implementing features. So sometimes you may not find a feature, or sometimes it may be implemented incorrectly, or sometimes a feature may be misinterpreted, right? So there are all sorts of issues, as you can see. So we started this project approximately 2017 summer. And since then, I should say that we have definitely improved way, way, way better as to how somebody can use the infrastructure, because it is not as simple as, you write a test and you compile and you catch the bugs and you report to the vendor, right? If one of you on the call were to jump in and use the test suite, it's our job to make it easy for you. So there are a bunch of, tools and scripts that will help you run the entire test suite and capture the, log files and save them in appropriate place, so on and so forth. So there is this background infrastructure that is happening on the in the back burner, which is equally important as creating test cases. Makefile and scripts, and design parameters, portability across multiple compilers and systems. That is another thing that we have to do. Keep in mind, we cannot write a test that is favorable to AMD compilers. So IBM guys are going to come and complain that, hey, look, you wrote something that is, favorable to a vendor. So the goal is to make sure that you create a, standard test case adhering to the specification and not really adhering to an implementation. Support for different compiler options. If you're a compiler person, you know that you have so many different flags. Sometimes a test would fail at the optimization level, for example, a -03, and it might work fine with default optimization. Those cases have happened too. So it's our job to be able to test the different test cases across different compiler options as well, because we don't know when it is going to fail. Sometimes we miss a certain scenario, and then we would, somebody is saying that the volume is low. I'm trying to take a sneak peek at the chat. Okay, I hope you can hear me. Sorry about that.
Sunita, volume is good actually.
Okay. Thank you, Ganesh. Okay, so portability across multiple compilers and systems, support for different compiler options, support for Lua like modules, batch schedulers, etc. Fast test, addition and modification, divided compilation and execution phases, and subset of test sections for partial execution. So as you can see, there are a bunch of permutations and combinations that we have adopted as part of the design process. Then this is a structure. I just thought to put it out there, to show you what sort of a structure we have as part of the test suite. Again, this is not set in stone. The compiler, the project has evolved since 2017. So you can imagine the number of, options and suggestions and recommendations we have gotten. And so we don't move things around too often. But if we get a major feedback, then we work around the structure and make it smoother, right? Because to us, feedback is very, very important. So for now, this is a structure that we are following, but it's, again, changed quite a bit in the past, I would say a month, but we are still trying to figure out if that's a structure we want to keep. So tests have different, testing feature folders. Then you have all those Makefile scripts and stuff sitting in another folder. And depending on which machine you're targeting, so Summit is currently the fastest supercomputer in the world, and Summit is in the Oak Ridge National Lab. Summit Dev is the baby Summit, but it's going to be decommissioned soon. Titan was a system prior to Summit, again decommissioned. As you can see, so basically these are different templates for different systems, and as systems grow, a number of systems grow, you're going to have more of these. Anyhow, so that is the overall structure of the test suite folder. And these are some of the machines and compilers that we are using at the moment. Level of support of multiple compilers and systems of the offloading constructs. So Summit at the Oak Ridge National Lab, as of this month, or maybe last month, we have started to use GCC 9.1.0. Clang Coral version based off a particular trunk, and then the Clang version 9, XLC, etc. NERSC is an entity as part of Lawrence Berkeley National Lab, and we use their Cori system. We use the Clang 11. I'm sure there are other compiler versions, but this is kind of a relatively newer system that we have started to access, so we're still in the testing phase. We have some local UDEL systems in my lab. Eureka and Obi-Wan, that's my students who have named it with these funky names, basically. Then we have different GCC versions, Clang versions. There are stable releases, and you don't want to test a compiler that is super new, right? Because there are going to be bugs. So we test a version before, we test a version of 2 versions before, to look at the path as to how the compiler has become stable over the past couple of versions. AOMP, AMD OpenMP compiler on Obi-Wan system, and I think we have an AMD Vega card, GPU card. Other systems, basically it is NVIDIA GPU cards. I think that is a V100 Volta, there is a Pascal 100. There are a couple of I think there is a GTX, but predominantly Volta 100 and Pascal 100 and Vega 6 AMD GPU. Right, so that's a simple, cartoon of Summit system. A single node of Summit has 44 IBM Power 9 cores. Ganesh, I hope I'm right on this, and 6 Volta V100 GPUs. It's a single node, and you have several of these nodes as part of Summit. And you see the little, the connections here, right? HBM is your high bandwidth memory. And this one is our internal system with Intel CPUs and NVIDIA GPUs and interconnections and all of those. Just an example of what do I mean by the test bed. Some results, they are not results from yesterday, but they are relatively recent results as of early this year. Summit compiler results. So let's see how to read this chart, right? So you have GCC, GNU compiler, IBM Excel compilers, and you have the LLVM compilers, CC++ Fortran, CC++ Fortran. So it is not just one programming language, but 3 programming languages there. And the percentage is how many passed, how many failed, that kind of a thing. So I don't know, I hope the Zoom window is not hiding anything. So let me see if I can move something. All right, so the blue one is the number of passes, so which is good. Compiler failure is the orange ones. Runtime failures are the gray ones. So again, the goal of the test suite is not to declare that one compiler is better than the other. That's not the job of, that's not our job, right? Our job is to report facts, report results, report output to the vendors, and seek feedback and make sure that what we have reported is correct to the best of our knowledge. So what you see is how the different programming languages perform from different compiler vendors on Summit. And again, the scenario changes every time a new compiler version is released. Like I said, we have a new GNU 9.1.0, so you don't see the bar chart yet. So it's likely that we have some more pass percentages. It's likely that we may have lesser pass percentages. So it's a process, right? Like I said, compiler is not a magic tool. It takes a lot of time and effort, to make it a tool that as customers, you're happy to use. So this is the Summit system at the Oak Ridge National Lab. So results of compiler installed in Summit system. That's technically our to-go machine, because Summit is used by many users, application users. So if you're a physicist, if you're a chemist, if you're a biologist, if you're an atmospheric scientist, and if you're using OpenMP offloading compilers on Summit system, you want your code to work, right? And because Summit is open to so many domain science users, we have to make sure that the compilers installed are in a stable condition. We have also all compilers basically, and different versions again. So another way of looking at the previous bar plot, and I think this is being recorded, so you can later on, go stare at these bar plots again, post me any questions you got. But that's another way to look at, Clang, GCC, G++, G Fortran. AOMP is the AMD, CC++ compiler, IBM's. This is a Coral version, another project within the US compilers. So sometimes vendors release a pre-release compiler version to test out. Sometimes it's a version that is open to everybody. So that kind of a thing. So, we can sometimes get compiler versions that is not open to you. For example, we make sure that it is tested, make sure it is doing the right job, and then it is released to you all. AMD, again, how do we read this chart? On the x-axis, we have CC++ compilers, AOMP, and the y-axis is the percentage of, how many passes, how many failures. AMD version evolution. So I like the word evolution here because, like I said, a compiler is not going to work fabulous on day one, right? It's an evolving process. And this is on one of our internal system, OB1. If you're wondering, oh, why didn't I use Summit? Summit does not have an AMD GPU. So we have resorted to using our local internal system. I think I hear, yeah, thank you very much. Obi-Wan, okay, so we see passes are all blues and the orange ones are failures. And as the compiler versions improve, we may see better numbers. So a publication that I would like to draw your attention to and is analysis of OpenMP 4.5 offloading and implementations, corrections and overhead, published by all of us together. There is a preprint available on ResearchGate. I can also send you the preprint if you drop me a note. But if you go to ResearchGate, there is a full PDF of this particular journal. This is published in Parco, yes, Parallel Computing. And this is one of my best to-go pieces that I would usually recommend people to go, because we put a lot of effort in this journal to give a very good perspective of where the compilers are. Now, this journal was published in 2019, late 2019. And as I said, this is stuff that improves on a daily basis, right? And as you speak, our test suite is running on Summit. So I wouldn't completely hold on to the results in this journal, but the process, the structure, the way we dealt with test cases, the correctness, the overhead aspects, using directives sometimes gives you an overhead. So what do we mean by that, right? And what compilers we have used, what systems we have used. I really love this journal because we managed to pull a lot of things together. A lot of day and night job went into this. There are 3 other papers that we have published, so you're welcome to look at that, but this is the most recent one. And this is a snapshot from the paper. It looks overwhelming, so don't worry about it. Go read the paper, and the table is in the paper. But what we try to list, and why do I really like this particular journal, is as you can see, we have about 88 test cases that we have listed. And at the time of publishing, these were the compiler versions, and those were the systems, Summit, Dev. Summit Dev is I think it's going to be decommissioned very soon. But prior to Summit going online, there was another system mimicking Summit. So I call it with my students Baby Summit, but the official name is Summit Dev. So we used that test name. So there's basically a continuation, okay? So test name and test name are continued columns. And these are the different versions. So you can see some passes, you see compiler error, you see runtime error. And if I were to take the test suite and plonk this on all these different compilers today, the table will vary a little bit, but I hope the table gives you the message of what we are trying to do. I wanted to draw your attention to our website. A lot of credit goes to my student Jose Diaz, who spent a lot of time putting this website together. We didn't have this website even until I think it's 2018 or 2019. But we started looking at different people interested, different people wanted to see where things are. So we were like, okay, it is time to put a nice website together. So CRPL, CIS, udel.edu, OMP solve results tab, which is first off, if you go to the website, you're going to get this page. And if you click onto the results tab, we have a nice little JavaScript there where you have the compiler listed and you have the systems listed. And when you hit on fail or pass or both, you are going to get a table like this. So you see a little box here, right? So there's a continuation of that box, and you're going to see which system, what compiler, did it pass, did it fail? And these results have been updated as of April 30th, 2020. So as of 2 months ago. So it's that recent. So take a look. So this is something if you people are writing test case or using a particular directive or feature as part of your application or teaching, right? And you want to see, oh, do I know if, for example, target parallel for SIMD, does it work? So one thing you could do is go check this website and see if it works. But as software engineers or compiler developers, you're not satisfied until you do it for yourself. So you could take the particular, copy of the test from the GitHub suite and run it in your own system, right? Your system may have different compiler versions. So you might want to check against that to see if it passes or fails. So this is the GitHub page. Again, I said it says open source. We get a lot of pull requests. Sometimes people go and check, hey, look, your test is not looking good. We found a bug. So you create a pull request. We look at your pull request And if we agree, both of us agree, then we merge. Or if we think, oh, no, this is what we meant, so we come back and we discuss with you, then we don't merge, right? But for you to interact with GitHub, you want to do a pull request. You can also add a new test if you like. It comes to us, we get a ping when you write a new test, then we discuss it internally. And if all boxes are checked, we accept it and it becomes part of the test suite. So that's happening a bit more lately, and I'm very happy about that, because initially it was just our team working on the test suite, and thanks to webinars like this, we are able to disseminate, the kind of work we are doing and get your attention basically, and look forward to your contributions and working together. There is also Redmine. We don't use it too much, but there is also the OpenMP ECP Redmine. I think this is pretty much my last slide. So that is the people involved, but I wouldn't, if you want to contact anybody about the test suite, feel free to drop me an email. I don't want to bug the rest yet, but if you're interested to collaborate or what have you, drop me a note and I will connect you with the rest. And this is a very important slide. I have to acknowledge US Department of Energy, DOE, Exascale Computing Project for funding us and working with us for over 2.5 years on this project. It's a collaborative effort. And thank you so much to all those who are involved. Anybody here wearing vendors hat, applications hat, users hat, developers hat, it all matters. So I'm glad to be talking to you about this. So I really thank you for your attention. So that's my last slide. Thank you. Yeah. I can take any questions.
Thanks, Dr. Sunita, for insights in OpenMP offloading and test suites. Really appreciate your time. Panelists and participants, any questions for Dr. Sunita? I also welcome Gopal Tadepalli, the senior professor from Anna University, to be part of this webinar. And he is also, acting as a panelist here. Let me unmute him also.
Mm-hmm.
Yeah.
Hello.
Yeah, go ahead, please. Go ahead, Professor Arghya.
Good evening from India.
Good evening.
Good evening from India, and what's the protocol? I just joined the panel, and what's the way we move about? I think Ganesh
please,
is
please go ahead with your question and answer, question, sir,
right.
About the presentation. Yeah,
I did. Yeah. Yes.
Yeah, go ahead, please.
Yeah, I did type in a question. The concern here is that concurrency is something that I wish to see more than parallel. It is something which we keep saying that it can collate several things that are happening rather than make it functionally definable as parallel threads. In all these cases, termination of all the concurrent threads is difficult to test and verify and validate, and therefore I have taken recourse to moving over to what Unix has as a zombie state. In case something has to be activated from the zombie state, we'll always pull it up. Is there something like that now happening in OpenMP?
That is an excellent question. Difficult to test for termination condition. Well, the test suite does not test such a condition. There are those implicit, I don't know if you mean the same thing, but once the threads finish what they're doing, there is an implicit barrier sometimes to make sure that all the threads have done their job, and you can move on to the next state. So are you asking about the testing of those implicit, explicit barrier conditions in OpenMP?
If it is only those post or preconditions or boundary conditions, then you are driving everything from a functionality, which gives you the parallel threads with as much clarity as possible. But in concurrency, they're already happening. I want to put them together. Becomes that bit more difficult. So how do we do that? We agree it is difficult.
Right.
What is the way out? What is the termination condition? How do you verify and validate?
I see. I don't know, to be honest, in OpenMP, besides the barrier conditions, but what I can do is look into this. If you drop me a note, I can get back to you. We don't test this particular condition. And I think what you're referring to may also be at the pthreads level, which is what OpenMP translates to. So there must be something at the pthreads level that is doing what you're looking for. So I can look into it.
Thank you.
Thank you, Dr. Gopal. Dr. Gopal, you can send me an email later. You know, I do have your email ID, and I'll connect you with Professor Sunita.
Sunita, that's nice.
Sure.
Great.
Okay. Any other questions for Dr. Sunita? Professor Arghya, yeah.
Sure. Thanks, Ganesh. And thanks, Sunita, for the nice presentation. And this is really great that you are doing all the tests on different types of hardware with different types of compilers. That's really great. Well, my research is not on the compiler. I am rather on the application side. So this is really, I'm very much interested in knowing the results. So first of all, my question is, I mean, do you have something for the distributed test suite, something like distributed test suite, like for MPI or something, or everything is only for OpenMP?
This particular project focuses on OpenMP. We have not tested distributed, you know, MPI plus OpenMP kind of features. However, you could look into the MPI world, and I'm sure they would have such tests, but the scope of this project does not cover MPI aspect.
Oh, okay, so all right, and well, yeah, I think that was my question. Okay.
Okay,
thanks.
Thank you.
Yeah, thank you, Professor Arghya and Professor Sunita. Any more questions, audience?
Matthias, I see your hand raised. Thank you for joining.
Who is that? Hold on.
Matthias Van Waveren, OpenMP. I see a hand raised. I don't know if that means they have a question or.
Yeah, that is right. Actually, they have a question. I'm trying to.
Ganesh, there are also questions in the Q&A section.
Yeah, I'm scrolling through those. I think one of the questions somebody asked, or Gopal asked us.
One of the questions is, do the test suites target only functional issues or performance as well?
Oh, I missed that. Thank you for asking. It tests currently, it's a good question. It tests currently for functional cases only. Having said that, the journal that I'm pointing you to has performance testing with respect to usage of compiler, you know, implementations. So the overhead aspect. So we have not tested the performance aspect itself, but more with respect to the overhead of using the directives. My master's student, Tom, is going to look into the performance analysis of the features. So hopefully by the end of the year, we'll have, you know, maybe a set of tests or maybe a publication that I should be able to share.
Thanks, Clarisse. Yeah, go ahead, Clarisse.
The second question from Alexei Batev is, do you have the results for Clang trunk?
Yes, Alex, thank you. I didn't see you have joined, thanks. Yes, I think we do. I need to go back and look at the results folder, but we have been testing Clang trunk pretty systematically. So if it is the same, yes, the short answer is yes. I can write to you. I'll email you. What are your plans for testing on other compilers? Matthias, I think we test already on AOMP, ICC, XLC. Is that what you meant? GCC. So the test suite is testing the compilers that is out there. So it covers what we have access to and what is loaded in Summit. Yes, Alex, I hear you.
Yeah, I think the Alex responded, yes, that would be good. Yeah. Okay, sure, you got it. Any more questions for?
V&V means validation verification. Somebody was asking, what does V&V mean? I'm just selecting questions which is, related to the topic.
Yes.
Collaboration, drop me an email. There are many different ways to do this, then we can chat up over email. Thank you for the interest. Distributed applications. Okay. What else did I miss?
I think that's any more questions from the panelists?
I wish to share something. The lecture was very nice, and all the reason why I wish to share this. My beginning in this exercise was to have an adaptation of ADA on data abstraction and concurrency on a 286. Difficult to believe, but there was a challenge. Well, it reached the summit, it hits the walls very soon. So gradually I moved over to testing it on a transputer farm. In all these cases, while I pick concurrency, the methodology doesn't change. We need to do something which can have a completion of the rule base for the compiler. How do you know that the rule base is complete in your exercise? Based on the rule base, you can tell me verification and validation, but how do you know it's complete? The methodology is the same. Or the grammar rules. How do we know they are complete? Where is the completion check for the grammar rules?
No, we don't do that in this particular test suite. That goes more into the lower level of the features itself. We don't get into those nitty-gritties, but I'm pretty sure that the vendors may be doing that under the hood. But we don't cover it from the testing of the directives and the compiler implementation itself.
Thanks. Difficult. It's a very important area, very difficult, but very nice, nicely presented. Thank you.
Thank you. Glad you like it.
Yeah. I think that's all we have, Dr. Sunita. Thanks for your wonderful presentation, and thank you again, for all your time spent on this. Thanks. Yeah. And I'd like to invite Clarisse, to do the second talk. Clarisse is actually going to give a talk about AI at scale, faster simulations, and better models and smarter deployments. It's all about AI, and Clarisse is an executive IT architect in the IBM Systems Worldwide Experience with the Center of Expertise on Application Performance and Benchmarking, as a senior member of Artificial Intelligence Center of Competency too. And she has got several, the customer related, experiences, and, she can she can certainly share, a lot of our customer experiences too as part of this talk. I'd like to invite Clarisse to start the presentation.
Thanks, Ganesh. Can everyone see my screen and hear me?
Yes, I'm muted.
I can.
Yeah, go ahead, Clarisse. Yeah.
So let's get started. I thank you, Dr. Chandrasekaran, for your previous presentation. I'm also going to start with COVID-19 and the pandemic. And the examples I'm going to talk about are going to be mostly related to the research that is happening in this space and some of the things that IBM is looking at to help the situation. So as we know, data and AI can make a big difference in the HPC world. And so this is a view of the HPC work that's going on, but also in the context of what data means to us in this space, as well as the opportunities for AI. So in particular, I'm going to be talking about some application areas and infrastructure that supports these areas in genomics, molecular simulation, biomolecular structure, medical diagnostics AI, data fusion and AI, as well as quality inspections. We currently have projects in all of these, and in particular have been doing a lot of work with the genomics pipeline and medical imaging diagnostics. Before I get into what IBM is doing specifically in terms of solutions, I wanted to bring your attention to the COVID-19 HPC Consortium. This is something that was started with the US government, as well as vendors and academia, to come up with a way to provide access to more and more resources, computing resources, for the study that's going on in finding a solution for the pandemic. So the consortium today has over 40 members, started off in the United States, but has contributors now from the UK, from Switzerland, from all over the world, that are providing cycles to researchers for COVID research. It talks about putting together different solutions. We have over 136,000 nodes in this consortium and 50,000 GPUs. So as I mentioned, it's coming out of the Department of Energy under the Secretary of Science. Dario Gil on our IBM side is one of the directors in our group that is supporting this effort, and it's across vendors, across universities, and there's a way to put in proposals for the work to get access to these resources. One example is the MIT work that you can see on the left. There are over 62 active projects and over 483 petaflops of resources that are available through this consortium. So I encourage all the researchers on the call to take a look at the website for the consortium. And if you have COVID-19 related research that would benefit from access to resources above and beyond what you have today, this is definitely a good path to take. So let's go back to the IBM solutions in these areas. Some of you have seen some of this already through a presentation as part of this webinar series by Dr. Linton Ward. This is going to be some of that same content, but also some of the later use cases that we've come up with and worked on since then. So genomics is about detecting biomarkers, doing visualization and statistics, and getting information from that. And it's typically a workflow pipeline that is important to get from instrumentation to insights. Molecular simulation is more classical or traditional HPC codes such as NAMD, AMBER, and so on, to look at modeling macromolecule receptors and small molecule ligands. Biomolecular structure is all about cryogenic electronic microscope images and looking at that information for drug design and discovery. Diagnostics is about finding patterns in medical imaging. Data fusion is taking data from lots of different sources, lots of structured and unstructured data, and gaining insights through AI systems from that data. And we'll have some examples of how we do that. And then finally, quality inspection is more a discipline across all industries, where if you can see defects, you can see them with AI, and these are tools that allow you to do that. So in terms of genomics and the genomics pipeline, the challenges here are that you need incredible accuracy despite ambiguity in the processes. The work that you're doing involves large data sets and long run times, and you need statistically large sample sizes to get meaningful discoveries. So the more organized you are along this work, the better you are off to get faster results. So it's all about time to science here, and being able to automate or semi-automate some of your integrated workflows makes a really big difference. So what IBM proposes is data insights factories. So this is part of our high performance data architecture, and it brings together storage, software tools, workload pipelines to get better efficiency overall. One of the use cases that we talk a lot about in terms of how all this comes together is Sidra Medicine. And they have, over the last few years, completed over 100,000 computational tasks that involve millions of files and directories and haven't experienced any downtime because of the fact that they put together this organized structure for their genomics pipeline. Let's talk about molecular simulation. This is all about modeling the virus. This includes looking at millions of atoms, trying to figure out the binding energy, predicting between atoms, between molecules. And IBM has a long history of traditional HPC simulations in this space. And the key here is to be able to leverage GPUs now to get accelerated performance and look at memory and network bandwidth so that you can scale to many, many, many servers. So in terms of scalability, this is a benchmark that we've run with NAMD that looks at ligands, and we've got 512 nodes here with good growth in how many nanoseconds of simulation you can do per wall clock time per day, so NS per day. And this is just one example at 512 nodes. We know that there's a lot of this work going on, for example, the Summit supercomputer, which is bringing this kind of work at thousands of nodes in terms of scalability. So while scalability is very, very important to get more performance, there's also a different approach or a complementary approach to simulation to get to end results in faster science, which is, what if you don't have to do all the simulations? So is there a better way to pick the simulations that you are doing so that you can get to results faster? And this is what Bayesian optimization brings to the table. So IBM is going to be announcing a Bayesian optimization solution, which is a state-of-the-art scalable solution that reaches across a broad set of applications. Any kind of simulation can benefit from this, and is easily organized and delivered via APIs so that it's easy to use. So again, here, instead of doing a lot of simulations, what you're going to do is find the parameters that help you define the next best simulation, so that ideally you're running fewer simulations and thus getting to results faster. We looked at this design by looking at what users are concerned about and what they need when they look at their large simulation challenges. The first challenge is not enough knowledge about the problem to build a good model. The second is getting better resource usage out of the resources that you do have so that you can do more science with the resources you have by reducing the number of simulations. The third is complexity and trying to figure out how to take advantage of tools that can help you understand your high dimension problems. And the last is trust, where you need to be able to explain your results so that there's trust in your results, and you can explain it logically. So a couple examples, and this is early starts. The program is kicking off, but we have some examples already where we're achieving human level performance in days instead of months, in the case of this accelerated force field tuning example. And in this second example, a third of the calculations were actually spent to achieve 4 orders of magnitude resolution improvement. So simply this IBM Bayesian optimization concept is that you co-locate an appliance, if you will, with a traditional HPC environment where you've got many, many nodes and typically a shared file system like IBM ESS or GPFS, formerly known Spectrum Scale today, where you're running your simulations on the large cluster, but you're using your previous simulation output to define your next simulation input. So to get this at scale, the appliance can also have multiple servers built in and GPUs to do this work. Let's move on to a biomolecular structure, and more specifically talk about the amount of data that cryogenic electron microscopes generate. These typically create 5 terabytes of image data per day. This is a huge amount of data, and basically keeping up with the analysis of that data today can be a very manual and tedious process. And so any type of automation or tools to help accelerate that make a big difference. So what we've done is used some AI techniques to improve the way that images are being processed. And in fact, we have a case here with the MIT Satori cluster, where more than 100 cryo-EM images jobs are running in parallel on the cluster. Another example of this type of work using the Relion standard benchmark, which is the software stack for analysis of cryo-EM. We could run on IC922s and T4 GPUs and reduce the time for the benchmark from over an hour to just over 30 minutes. What you're going to use in terms of system for this really depends on the amount of samples per day that you need to process with your instrumentation. So this is just examples of small, medium, and large configurations. They all have in common a server with GPUs, a storage subsystem, a shared with shared namespace, and a decent high-speed network, in this case 10 gig. We also take advantage of SMT, simultaneous multi-threading, which allows you to have more threads than physical cores to accelerate your workload. Moving on to diagnostics, medical imaging is key in diagnostics and medical research. The idea here is to take out some of the automated routine tasks and automate them, get some consistency in outcomes so that people are looking at the images with the same critical eye in that sense, and basically accelerating the end-to-end process of evaluating medical images. using deep learning and convolution neural networks, the state of the art for AI and visual recognition, whether it's classification or object detection, has greatly improved since about 2012, where this technology basically saw a rebirth in advantages, as it could beat the human eye at this point. So there's a lot of options here to take advantage of that. Some of it is depending on the type of data that you have. These are 3 examples. In the first case, it's the input is basically an iOS device or an Android picture, where you're taking a picture of a skin lesion and getting a quick feedback on the likelihood of melanoma, atypical or benign, which can accelerate and improve the next step, whether it's biopsies or monitoring and so on. Very simple visual model based on classification and learning from existing data. The second example is a brain tumor, looking at finer details in the structure of the brain tumor using a 3D segmentation model. And this model in particular was able to leverage large model support, where your images actually have much higher resolution and need more bandwidth and compute power to manage. And the third example is based on blood slides and looking at blood cell subtypes that also are used in diagnostics of blood-based diseases. Bringing this back to COVID, there are many efforts to make data publicly available so that these types of new research advances using AI can be done. This is just an example of public data set of lung x-rays showing COVID pneumonias, regular pneumonias, and normal lungs. And you're able to train a model that detects the likelihood of what you're seeing on those x-rays. And in this case, we were using Visual Insights, which is a point and click package where you don't need to be the data science expert in convolutional neural networks, but you can be an SME, and as long as you can categorize what you're seeing, you can train a model very quickly to detect what you're looking for as the subject matter expert. That type of technology in terms of evaluating, in this case, MRI images, was used with Washington University School of Medicine in conjunction with Vanderbilt School of Medicine. And they were able to train a model in just 2 hours compared to the 40 hours that it was taking them prior to taking advantage of the IBM medical imaging solutions that we provided. Let's move on to data fusion. This is also applying AI to medical research field. And what I wanted to highlight here are a couple things. One is an AI appliance by our partner Novi Systems. This is a company in RTP in North Carolina that has built not just a set of piece parts, but a solution that is easy to understand, focuses on what the subject matter expert can do as opposed to the under the covers work of IT and data scientists. And that basically takes all information from a lot of different sources and gives you enough analysis so that you can answer questions via natural language processing and machine learning and get answers very quickly. So under the hood, it's basically using AI and analytics, taking data from multiple different sources, whether it's text, databases, sensors, or images. It's applying those AI techniques to those data sets and developing fact tables against which the subject matter expert can ask questions and get actionable decisions as a result. I'll put up this website, which is one example of how this appliance is being used. And again, COVID-19 related. It's basically a search of published data and lets you get a lot of information very quickly from a lot of different sources on COVID-19. So if you go to that website and look around, you can get a lot more information about the virus and patterns that are emerging from published publications, research publications. The second piece of solution that I wanted to bring up relative to data fusion is all the work that we do on the storage front and building an enterprise data pipeline for HPC and AI. So it starts with data in, coming from instrumentation, from the edge, from various sources, and it goes through different stages to get to insights. And that's ingest data, organize, analyze, apply AI, and get insights. The distinction that I wanted to point out here in terms of what all these components are is that some are capacity tiers, some are performance tiers, and some require both. So depending on where you're getting your data, what you need to do with it, you may need to choose different aspects of the overall IBM storage solutions to fit your use cases, whether they're traditional or new. And I'll point out specifically the data lakes that are performance and capacity, where ESS and spectrum scale play a big role. And I'll mention also the classification and metadata tagging, which takes your data to the next level. So instead of, in a sense, storage that's just storage, you also have information about what you're storing saved in this architecture. So more specifically, we have products that apply to each of these. I mentioned spectrum scale, which most HPC clients may be familiar with the FIT shared file system, parallel shared file system. Cloud object storage is great for capacity. Spectrum Discover is what we use to provide metadata and tagging. This is very important in the AI space to find the right data that you need at the right time to build up your training data sets. And of course, we shouldn't forget archiving with cloud and tape solutions, as well as Cloud Object Store for that as well. Finally, let's cover quality inspection. This is, again, an AI use case. And the example here that I'm going to cover is about pulling it all together through a quality inspection system. There are data scientists that are involved here with building the right models, model engineers. There are edge managers that deploy and manage the edge devices where your models live to do inference, that is to get results. And you have systems in the back end to store your data, to create actions based on results, and to automate a lot of the inspection workflow. One example of this is a combination of Visual Insights and Visual Inspector. We talked a little bit about Visual Insights earlier in terms of building a model to classify an image or detect an object. You can take those models and download them onto an iOS device with Core ML, and we have a App Store application called Visual Inspector that has pre-built dashboards and systems to collect data and to inspect data. We see this used in a lot of different cases in the life sciences, healthcare, pharmaceutical use case. One easy example is in medical products and consumer packaging of drugs, where you can look at your supply chain, decide at what point you do need inspection points, and where you can apply visual models for those inspections. So again, it's about automating and accelerating the inspections and getting more accurate information on finding defects or anomalies or just sorting patterns of whatever it is that you want to inspect. So to conclude, we talked about using the high performance data architecture to merge HPC, AI, and cloud so that we can collaborate and address these critical challenges that we're finding in medical research, in particular with the COVID-19 pandemic work that is so critical to get to answers and to get to science faster. We showed you some IBM solutions. A lot of our solutions are also open source and take advantage of the entire ecosystem. So we encourage everyone on this call to take a look at those more closely based on your area of interest. We have a full infrastructure that starts at the data, where we talk about data for AI and our solutions in that space. We didn't spend too much time on workflows and job scheduling, orchestration, and virtualization, but we have those tools available as well to orchestrate your environment. We have applications and models and expertise to help you build out AI and how to apply it to your HPC traditional work, such as using Bayesian optimization. We have other tools to get insights from your data, like the data fusion examples. And then finally, we've got the expertise from the industry perspective on how to apply a good, solid IT infrastructure to your genomics, molecular simulation, structural analysis, diagnostics, data fusion, and quality inspection areas that we talked about today. So I will conclude with some extra links and an offer to work with us on your opportunities with HPC and AI to build solutions together. And I wouldn't be here if it weren't for our extended team, which is the folks below here, as well as our clients and partners and our researchers that are pushing the limits, as well as all our product support colleagues that are building these solutions for us. That's my last chart, Ganesh.
Thank you. Yeah. Thank you, Clarisse, for the wonderful presentation and also sharing your experiences on, the IBM Power 9 system with the various applications and, the platforms and all. Thank you very much. Audience, any questions for Clarisse? Panelists, let me open up, Dr. Gopal. Since he asked some,
thank you
he posted
again.
some questions. Yeah.
You see, I did post. The concern here in medicine is that the medical doctor has a belief system which refuses to be coerced into any data representation first. That is the first concern. Now, what we are getting started with is a data representation. We struggle to get out of structuring. We are now in big data. But that gap between what a medical practitioner begins with, that's a belief in what he thinks is diagnosis, which refuses to get coerced into data. That's the concern. How do we address it?
Yeah, so that's probably a bigger question beyond what the IT infrastructure can provide, because you're right. What we're providing is augmented intelligence. It won't change necessarily the culturally ingrained workflows of doctors. The only thing I can say is that we're seeing a lot of consortia, like the radiology consortia, are recommending that using AI can augment a doctor's capabilities. So there's a lot of regulation and a lot of proving out that still needs to be done on specifically on using AI in diagnostics. And that's why researchers are the first ones to start looking at this, so that eventually it becomes a clinical practice to take advantage of AI.
Expert systems? Is
Yeah.
it what is going on in your mind? Maybe yes, we'll get them now.
Right. That putting AI into expert systems, for example, is one of the goals. I see a question on what is metadata. So metadata is basically descriptions of your data. So for example, if you have an image of a lung X-ray, you could tag that image with any level of information that you want, so that in the future, when you need to find that image again, you have the metadata, you have the information about the image that you can pull in quickly.
Yeah, there is a question on the the attendees side also. Hold on. Let me Shanti Prabha. I think let me allow her to talk. Yeah, Shanti, can you go ahead and talk? Shanti, can you hear me? Looks like I don't know what happened actually. Maybe let's move on. Let me allow Gautam Kumar to talk. Gautam? Oh, there are a lot of people raising their hands actually, but I don't know what's happening here. Hold on. Ask to unmute. Gautam, can you unmute yourself? Hello. The participants, actually, those who, if you have any questions, I'm actually allowing you to talk, on the tool. Please go ahead. And Gautam, can you hear me?
Yes, yeah.
Yeah, please go ahead.
Hello. Actually, I asked my question to the man. Hello.
Yes, go ahead.
Yeah, go ahead, please.
Actually, I asked a concern with Sunita ma'am, but she replied it. That's why I raised my hand.
Oh, okay. I'm sorry. Actually, yeah, I didn't know that. Okay, sure.
I
Thank you.
see a couple more questions on accuracy in using the AI tools. So one, and I mentioned earlier that using visual models have improved from being not as accurate as human eyes to being more accurate by a few percentages. So with a well-trained model, the predictions can be as good as human predictions when looking at images. So there is really potential for leveraging these tools, not as replacements, but to augment um, the subject matter experts. The other thing that these AI tools can do is it can take the best subject matter experts in a field and train against their knowledge so that these models can help other practitioners that may not have as much expertise, or in a staging way get a first pass through maybe lab technicians and so on to evaluate images to get results.
Thank you, Clarisse. And any more questions for Clarisse? Audience, panelists?
So, Clarisse, I have a question on the Bayesian simulation. So,
Yes.
yeah, so you told that this Bayesian simulation is done over multiple CPUs and multiple GPUs and like that. So, how is this? I mean, I don't know whether this is question for this seminar or not. How is this Bayesian optimization is being used in the simulation? So is IBM using some kind of a big Bayesian network, something like this, or some Bayesian function is just being used as an optimization function or like that? Do you have some details on that?
Yeah, so the Bayesian optimization is about evaluating results from previous simulations and looking at the parameters that go into the simulation. And so it's optimizing against the next best set of parameters. And it's you need multiple systems when you've got a lot of simulations, so it's to accelerate the throughput of those. But I think taking, since it's not announced yet, taking a discussion offline is probably better to go into more details on how that's all going to work and how to try it out.
Okay, thanks.
Yeah, thank you, Professor Arghya. Any other questions from audience as well as the panelists? Oh, okay, I think, you know, we're not getting more questions. Thank you, Clarisse, for, you know, for the wonderful presentation again. You know, thanks for your time on our webinar too. Really appreciate it. Thank you. And you know, again, you know, I'd like to thank the presenters for the presentation today. Thanks to Dr. Sunita, Chandrasekaran, and Clarisse, Hedglin. Thanks to panelists, Professor Arghya, as well as Professor Senthil. And also thank you to all the participants who stayed for last, you know, more than like, you know, 1.5 hours, and also actively participated in the webinar. And looking forward to meet you all on June 19th webinar with the University of Brasilia and also European partner. I will share the invitation, you know, with you all. And thanks again. And I'm closing the webinar now. Thank you.
Thanks. Bye.
Thank you, Clarisse. Thank you.
Thank you. Bye.
Thank you, Sunita. Thank you.